Hello and welcome to the first lecture of this course of Survey of Plasma Physics. We will be talking about plasma physics and we'll be following the textbook by Garnett and Bhattacharjee, Introduction to Plasma Physics, but we'll also make some modifications as needed. Now, our textbook, like most textbooks, like most courses, start with the question, what is a plasma? That is not something I'm entirely happy with. So we're going to do something different. We're actually going to call our course something else. And we're going to call it, or rather, we're going to start with a different statement or question, and that's going to be, what is our definition? Let's see if I can spell it right, of a plasma. That comes from my preference to try to remember what is it that we defined rather than what was the question, we want to know the answer. Very well, then what can we do to define our plasma? Well, it turns out that the definition can be a little less neat than we would like, or rather can make a very precise definition, but then we may be in situations where it's not necessarily so clear that where we are with our system. Is it a plasma? Is it something else? And in fact, that's part of what makes teaching the initial part of this course a little less fun than other parts, because we have to focus on the details of the definition. What is it that we're studying? In fact, no, that's not really true. This part is apparently boring, but it's actually very important, very fundamental, because it is what is going to allow us to understand what we're working on, what we're working with. And there are also different types of plasma, so that a definition that applies to one of them will not necessarily apply to all of them. But let's take this one step at a time. My first step for a definition of a plasma is going to be that a plasma is an ionized gas. Now, this may or may not already make you think of what might go wrong with this definition. Plasma, as you've certainly heard, is the fourth state of matter. Okay, what are the other three? Well, we have solids, and then we heat a solid up. When it gets warm enough, it turns into a liquid. Then we keep heating the liquid, it turns into a gas. We keep heating the gas, and it turns into a plasma. Very simple, very, very clear. But what about something like a piece of ice? We touch it, it's wet. Okay, well, the temperature is above freezing, but we have this piece of ice. Well, we see it's solid, but it's also wet, so it's also liquid. Or maybe we had it in our glass and it melted, and we still see there are some little pieces of ice, but it's mostly water. So which one is it? Is it now a liquid, a solid, or something else? And that is what I was referring to, what may make a little ambiguous our definition. But we'll give a clear definition, and in most cases, or in all cases, I should say, for what we're going to look at in this course, there isn't really going to be any doubt about, is this a plasma or not. We're just going to look at plasmas, and we may from time to time emphasize, okay, why is this a plasma? In fact, when we talk about plasmas, the usual definition is definition of a fully ionized gas. But then we almost immediately, or perhaps we should immediately be aware of the fact that there are plasmas that are not fully ionized. And there can be even be plasmas that are weakly ionized, but we'll still consider them plasmas. So that is not all there is to it. One element that is important in defining what a plasma is that the plasma is some type of a fluid that is dominated by collective effects. I'm now going, and for the rest of the course, I'm going to be mostly handwriting. My handwriting is not my strongest suit, so I will apologize for anything that may create issues. But please go back to the notes in the textbook, and you shouldn't have too much trouble following. Now, I was saying plasma needs to be dominated by collective effects. And that immediately tells me I need enough particles to make a plasma. Two charged particles, an ion and an electron, do not make a plasma, because there isn't anything collective about only two particles. And this is an important difference with respect to gases and liquids, because even though those may at times and maybe often exhibit behaviors that are in some ways analogous to the behaviors or related to the behavior of plasma, those are dominated by collisions with nearby particles. Is a gas or a fluid behave as a collection of particles because nearby particles can collide, interact, and communicate with each other. Plasmas can be pretty close to being collisionless. That's particularly true for fusion relevant plasmas. And as such, are not dominated by collisions with nearby particles, but by long-range effects, which we'll get into a little at a time. Another important property of plasmas is that typically plasmas tend to be quasi-neutral. And here too, we may try to be extremely precise by what we mean by quasi-neutral, but a general intuition, a general understanding is going to be sufficient for our purposes. Quasi-neutral means what you could guess, that the in general, the charge in a finite or small volume of plasma is pretty much zero, the total charge, at least a steady state. That also implies that small electric fields are all that's going to be possible at steady state, at least over short distances. Now, what small means will have to be clarified, but we are not going to consider in general as quasi-neutral a plasma where there is a significant excess of one type of charge with respect to the others. And keep in mind that in some fields of research, there are plasmas that are very far from quasi-neutral. Some types of plasma may only have one type of particle or be completely non-neutral. For instance, in other fields, plasma that are made just of electrons or just of ions, or to make it even more exciting, just of positrons or antiprotons are used. And their purpose is to study some details, for instance, collisions and the behavior of strongly coupled plasmas. We'll eventually get to what we mean by strongly coupled. Okay, then we're hopefully starting to think of a plasma as a fully, or at least significantly ionized gas that is, for what we're going to be interested in, quasi-neutral and dominated by collective effects. That should suggest that a good way to handle this type of system may be something like statistical description. Now, I'm going to handwrite distribution function that we're going to see a lot. And I'll do that expecting that you're already familiar with it from statistical mechanics. Because of something called the H theorem, system in thermal equilibrium will occupy the most probable state, and that state is described by Maxwell-Boltzmann distribution function. So the H theorem implies Maxwell-Boltzmann, which, as you most likely already know, looks something like this. F, where F is my distribution function of velocity, is equal to some normalization constant times m divided by 2 pi kt to the power of 3/2 times the exponential of minus mass times velocity squared divided by 2 kt. I will give you a disclaimer at this point. Often, for convenience, in plasma physics, people neglect to include the factor K. Which is going to be either implied or absorbed in the units of temperature. I will do the same and express the temperature in energy units, but depending on the situation, you may find both energy expressed as Kelvin or some other unit. Typically, we'll use electron volts. My units for temperature are actually going to be electron volt, which correspond, and I'll let you verify that for an exercise, to 11,600 and change, 604 Kelvin. As a note, Kelvin are not degrees. It doesn't really matter all that much, I suppose, but if you are a purist, you know that we use multiple different units to measure temperature, and we could use degrees Fahrenheit, or we could use degrees Celsius, or we can use Kelvin, which are one of the fundamental units of the international system, and as such are just defined by their name. Now, coming back to the expression I wrote up here, V is, let me make it perhaps a little bigger for a moment. There we go. V is going to be velocity. And here I'm just writing velocity as a scalar, because the form of the distribution function that I wrote is isotropic, and that means it does not depend on the interaction of the velocity, only on its magnitude. But in general, the opposite may be true. The distribution function may depend actually on the direction of the velocity, not only on its magnitude. M is going to be the mass of our particles, could be ions or electrons, and that also tells you I'm going to have one of these distribution functions for each species in my system. And then, well, pi is pi, and it may not be readable. So let's see if we can do anything better. I've already told about the Boltzmann constant, and that's all we have in this expression. Now, in general, things may go differently. And as I said, temperature could depend on the direction, and the Maxwellian itself may depend on the direction of the velocity. That is, Vx, Vy, Vz may not appear all in the same way, or the distribution function may not be invariant for rotation of the axis, a change of the axis from where I get the x-axis to overlap with the z-axis, and you keep the right-hand rule to figure out which one goes where. Well, before I write it, in general, one case that can be important is the case where temperatures are different along and across a strong magnetic field. We will look at the situation where magnetic fields are present in the system. A strong magnetic field will strongly influence the behavior of the plasma, and the behavior along the magnetic field may be rather different from the behavior across the magnetic field. And for that reason, we may end up with something that is called bi-Maxwellian or B-Maxwellian. That's going to look something like this. I'm going to have my function, distribution function, function of the velocity, and that's going to look a little different from what we had before. I'm still going to have that normalization constant and 0. And then I'm going to have square root of 2 pi times, I'm going to define these quantities shortly, something I'm going to call V thermal parallel, times a similar expression where I have square root of 2 pi times V thermal perpendicular, and this is going to be square. And then I have my exponential that's going to have in the exponent minus Vz squared over 2 V thermal parallel square minus Vx squared plus Vy squared divided by 2 V thermal perpendicular squared, where I have assumed that the magnetic field is in the z direction. Okay, this is a bit of a monster, but let's see what we can do with it. What does it mean? What I mean with the symbols V thermal and V parallel is the following. V parallel is going to be equal to T parallel divided by M under square root, and analogous for V thermal perp. This is actually a definition. This is the definition of this symbol, and you see that my Boltzmann constant has disappeared in here. Now, these are my thermal velocities. They may be represented with different symbols. Sometimes you may hear people may loosely refer to them as sound speeds, but the important part here, as in everywhere, is that we're clear on what we mean by what words, not quite the words that we use. Okay, this may be a little surprising because we're very much used in fluids to think of temperature as a scalar. But it turns out temperature, as you already know, is a measure of the average kinetic energy of a system, gas or fluid or liquid or plasma. And it turns out that the kinetic energy or the average velocity square along the magnetic field can be rather different from the average square of the velocity or the part of the velocity that is perpendicular to the magnetic field. And that's how we can end up with two different temperatures. Now, that's great for complicating things, but it's also going to be, in general, true for either species. And that is, ions and or electrons can have different temperatures in different directions. But ions and electrons can also have different temperature among themselves. That is, the temperature of the ion in general can be different from the temperature of the electrons. Now, this may be a little surprising, and you may wonder how general the statement is. Well, that is a good question to ask. You will want to check how related the two temperatures are in this specific system you're looking at. But I want to emphasize that in general, even at steady state, there is no guarantee that the two will be equal. And we're not quite going to get to the details of that, but let me just give you an idea of how that can happen. In a system like a fusion reactor that runs a steady state, if you've heard of them, think of a tokamak. If not, we'll see what a tokamak is. It's a container with magnetic fields, ions and electrons that get heated to a temperature that's large enough for the ions to start having fusion collisions. Fusion collisions create, depending on the fuel that you're using, new particles that are going to have much higher temperatures or kinetic energies than the ions. And then those particles will collide with ions and electrons, but they're typically going to heat the electrons first, and then the electrons will heat the ions. And since you have at steady state a constant source of those very hot particles, will be alpha particles, you're never going to reach a situation where all the temperatures are the same, because you keep creating hot particles. And therefore, you can easily end up in a situation where the temperature of the electrons is higher than the temperature of the ions. What the equilibrium temperature or the steady state temperature is will depend on the details of the system. But I want you not to get confused and blindly say, assume that temperatures are the same when you have no reason to do so. Now, one more thing. These thermal velocities are defined as shown as square root of temperature over mass. You may wonder if those are the average velocities of your particles in the system. And that is, in fact, a good question, which I'm going to leave as an exercise or homework problem. One more thing that we may want to be mindful of is that in general, this is not the only type of distribution function you will find in your system. Yes, I know. I did start by saying that the H theorem says at steady state, and that is what you're going to have. That's all true, but think again of a system where you have a source of particles at a certain temperature or at a certain average kinetic energy, as in fusion products. Well, then what those particles are going to do once they're created is to start slowing down by collisions. And at steady state, you'll end up with a distribution function that does not quite look like a Maxwellian. I'm going to leave it at that for now, and we'll see if we can get back to this a little later. Now, let's move on and consider something more about what we started saying, the collective behavior of a plasma. And in particular, we're going to look at something that is called the Debye shielding. Let's see how that comes around or about. What recap? Thank you. What we start from is our plasma with some ions, some electrons, and quasi-neutrality. Everything works great. But then we say, well, what happens if somehow magically I can make another particle appear in my system? That particle that I'm going to call either a test charge or perturbation charge. But be as it may, it's a point charge, just magically appears in the middle of my until then quasi-neutral plasma, and we want to see what's going to happen. Well, we have now a charged particle, an excess charge. We should not be surprised by the fact that we should actually, what we should expect is that there is going to be an electric potential. We're going to assume that this is an electrostatic potential. So I'm just going to use the letter phi to indicate it. And it's a scalar, it's electrostatic, and this is the scalar potential, electric. And since all the particles in my system are charged, I can immediately realize that particles in general, we have total energy, that each particle will have a total energy that looks something like this. There is going to be the kinetic energy, and then there is going to be the energy due to the electrostatic potential. You most likely see where this is going. We go back to statistical mechanics. And from statistical mechanics, we know that the distribution function, which I'm now going to assume to be isotropic, is, for simplicity, is going to look something like this. It's going to have my normalization constant. And here, for a change, I'm going to include the Boltzmann constant. So I'm going to have 2 pi kt all at the power of 3/2. And in the exponential, I'm going to have e to the minus w over kt. Or if I copy the expression from above, that's going to look as follows. Going to have n0 times m divided by 2 pi kt all to the power 1.5 times the exponential of m minus mv squared over 2 kt. And let me write this separately, times another exponential that's going to have the electrostatic potential and then kt in the denominator. Okay, now we have to be a little careful and be mindful of a subtlety that is well emphasized in our textbook. That is that if I want to know what the system is really going to do, I actually have to solve an equation for the distribution function that is coupled to the Maxwell's equation. I can't just assume what my distribution function is going to look like. I have to confirm that is the correct behavior. But for the purpose of the current discussion, we can take this expression as correct. It is correct within certain limits, but it is sufficient for what we're trying to accomplish. Then I'm going to assume that ions do not move. Okay, this is a little delicate again. Welcome to the world of plasma physics, where everything is a lot more subtle than you may think. Now, what happens here is that I'm going to ignore the motion of the ions, and that is a legitimate thing to do under certain assumptions. But I'm not going to tell you what the assumptions are, because that's going to be an exercise in a common problem. You have to see what is it that allows me, what conditions would allow me to assume that this is a reasonable behavior for the ions. Be as it may, I'm going to look for a solution of the Poisson equation. What I'm trying to solve for is the electric potential now, because I wrote my expression in terms of the electric potential, but I don't know the shape of that electric potential as a function of space. And so I'm going to try to solve the Poisson equation, which I'm going to write as follows. And del square of phi is going to be equal to minus E electron charge. I'm going to assume that ions are singly charged, divided by epsilon 0 times the difference between the number of positive charges and the number of negative charges, or rather the number of ions and the number of the electrons. Now, since I'm using a point charge, it seems reasonable to use spherical coordinates. That's not the only way to do this derivation, but it's the one that's in our textbook. And for that reason, that's the way we'll follow. Now, what I have to do is to express that del square operator in spherical coordinates. I can pick it up from a textbook or a table of differential operators. It's going to be in the plasma formulary, which I highly recommend. You can download it for free from the NRL website. Anyway, before I do that, let me do something more. I'm going to assume that there isn't really anything else going on in my plasma. My plasma was there, just sitting happily. There is no magnetic field, no other disturbance with respect to the isotropy and homogeneity of the plasma. And that leads me to think that spherical symmetry is probably going to be a very good assumption, because there is nothing that breaks the symmetry. I have a point charge. I'm going to set it at the origin of my axis, and there is no angular dependence. That means that my equation is really a one-dimensional equation. Everything is only going to depend on the distance between the test charge that I put into my system and the point in space where I'm looking at the solution. Okay, then I'm going to replace my del square phi with just the radial part, which looks something like this. I'm sure you've seen this in other courses. And on the right-hand side, I'm going to have the distribution function of the ions and the one of the electrons. Now, I did say that the ions do not move, and I did that for a reason, because now I can say, well, okay, I'm going to have N0, it's going to be a common factor, I pull it out, times E, electric charge, divided by epsilon 0. For the ions, that's all there is to it, because I have N0 ions. That's the number of my ions. And for the electrons, I'm going to have this extra factor, e to the E phi over KT, where I'm using the fact that the charge of the electrons is equal to minus C. So I replace the charge. Okay, this looks like fun, right? How on earth are we going to solve this thing? Well, there is quite a bit of work to be done, but there is one thing that we can observe that's going to help us. I keep insisting that plasma is going to be dominated by collective behavior, long distance behavior. I haven't quite quantified what I mean by long distance. Long with respect to what? Well, here's where we're going to get to it. Yeah, I'm going to say, well, I'm going to assume that the electric potential is small. I'll never be tired of stressing this point in physics. When I say that something is big or small, I need to specify with respect to what, otherwise the statement has no meaning. But here I'm going to assume that the electric potential is small enough that this ratio is going to be much less than 1. So of course, I'm going to expect, well, the potential is going to blow up when I get close enough to my particle. So maybe that's not such a great assumption. Well, I'm just going to look far enough from my particle, and then I'm going to be able to use that assumption. Okay, then what happens? Well, if I make that assumption, I can, let's make a nice arrow here. I can Taylor expand this quantity here, this exponential. It is not going to be too hard. Goes to 1 plus E phi over KT. Then you put all the pieces together. This one and this one cancel. And I'm going to end up with an expression that is now going to be linear in phi. Okay, then I can replace this expression up in my brackets, and that gives me the equation to solve. Oops, sorry. Forgot to change my pen. 1 over r, second derivative with respect to r square of r times phi is going to be equal to, okay, I have n0 e square e times e. I'm going to put in the side by itself. Then I have epsilon 0 k e, and that's all there is, times phi. I'm just going to leave this temperature as T, but strictly, since I said that ions do not move, what I really have to consider and look at is the temperature of the electrons. But again, for simplicity, I'll just mark it as E without a subscript. Okay, well, can we solve it? The answer should be a happy yes. let's see, you can, there's various things that you can do. I'll let you work on it, and I'm actually going to show the behavior of the solution for something we're interested in. But before I do that, I realize that this quantity that I'm going to put in brackets now must have the dimensions of an inverse length square just by dimensional analysis. And I'm going to give it a specific name. I'm going to define lowercase lambda subscript d square to be equal to epsilon 0 kt divided by n0 e square and this is going to be the square of the Debye length. This is the name we're going to give to this quantity, right? Introducing this notation and this name for this quantity. Now, it's going to be interesting to look at the solution. What does it really look like, and how? What are we learning from this expression? So let's go open up Mathematica and let's see what happens. All right, then. What do we have here? Maybe I need, should be visible enough, but yeah, I don't think I need to make it bigger. Now, if you're not familiar with Mathematica, that is a great tool to use for symbolic calculations. I use it all the time. May not be the fastest tool in the bunch, but it may be the sharpest, depending on what you're trying to do. What we're trying to do now is saying, well, what are we really dealing with this equation? And here, the first thing I'm trying to do is to tell Mathematica, just solve this differential equation. That's the equation I started from. Here, I'm replaced the factor n0 times e divided by epsilon naught with the Greek letter alpha, and the factor e divided by kt with the Greek letter beta, and I'm calling my unknown f of x just for simplicity of typing. So here is what I'm doing. I'm asking Mathematica, well, just solve this equation. I don't believe the textbook. I'm sure it can be solved. I don't know how to do it. I'm sure it can be solved. And here's the answer that Mathematica gives me. So the expression says d solved, blah, blah. Which means the Mathematica doesn't know how to solve it. There is no closed form solution that we can find with standard methods. I should mention that occasionally we will encounter, maybe not in this course, but it does happen that you may encounter some problem that Mathematica cannot solve, but that actually does have a solution if you're clever and creative enough. But in this case, really, we're stuck. Well, then, what I do next is take the Taylor expansion. The equation I'm solving here is the equation with the Taylor expansion, where alpha times beta is the lambda by square. And you see that this is the answer that I obtain, which is a little messy. If you have the textbook close to you, well, that's not what's in the textbook. And in fact, what you're expecting to find is only the first solution. This is a second order equation. You get two solutions, but only the first one is the one that we want to use. And I very much hope that you can see why. The reason is that the other solution, the one with the e to the positive x times lambda over lambda by, sorry, is growing as we move away from the charge, which is unphysical. It's not what's going to happen in reality. That solution shouldn't be there. And it also violates the assumption that we did at the beginning that my my term in the exponential containing phi was going to be small. Well, this term goes, if we pick the second solution, the term goes to infinity. So that is not a good assumption. Okay, then the solution is actually going to look like the first one, but how well does it work? Well, one thing that I can do is take Mathematica and ask for a numerical solution of the potential. Now, normally or commonly what we do when we do this type of calculation is say, let's start from x equals 0 or r equals 0 and integrate outwards. Now, this equation is going to run into some serious trouble because I have the 1 over r terms. So I'm going to start from r equal 10 instead, or rather 10 lambda d, 10 times to the bi-length, and I'm going to integrate inwards towards 0. And let's see where I need to stop. Okay, so here is my numerical solution. If you have not seen, I believe you should all have, but if you have not seen any methods for solving differential equations numerically, don't worry about it. There are commands in Mathematica or other languages that will sort of do it automatically. The whole idea is I'm going to try to build an approximate solution to my differential equation by figuring out point by point on a certain grid what the value of the function should be and approximate my derivatives with finite differences between values instead of log limits and so on. At any rate, that's what I do. Oh, I should mention that I've defined this function here as the solution I actually want, so which is this function there. And then I just make up values for my constant. It doesn't really matter what they are as long as they're not 0 and not them go to infinity. And then I'm going to tell Mathematica, well, let's assume that the solution, the approximate solution of a calculated explicitly is correct away from my test charge. And let's try to do a numerical solution that start from some point with the same value as the approximate one, and let's integrate inwards and let's see if they really look the same. Now, I do get an error message, not something we often want to see, but what this is saying is that the numerical solution starts having problems if I move too close to the origin, that is to the position of the charge. And up to that point, the solution looks something like this. Okay, that's not really telling me all that much. Now, what I'm doing here is extract the functions from the solutions so I can plot them. And well, let's see what the plots look like. Here I have a linear plot in linear scale. You see that the vertical axis goes from 0.2, 0.4, and so on. And the blue one is the one I'm plotting first, which I now don't remember if it's it's a numerical solution of the complete equation, and the orange one is the approximate solution. Well, they look, until I get too close to 0, they look pretty similar. Here they look essentially the same. But let's make sure that that's really so. Let's just try to plot them in a different way with a log scale, or a semi-log scale. And you see that really they're pretty similar. Here I'm going to plot the relative difference between the two. And you see that it starts from 0, as it should, because I'm assigning as initial condition for my numerical solution that the two are identical at this point. And then the difference between the two grows, and it starts growing fast once you get here. Let's see, do we want to? Why not? Do you see the shape of this difference? It looks kind of weird, right? What on earth is going on here? What's this ladder with steps that, or staircase with steps that become smaller? This shape is due to the way Mathematica is doing the numerical solution. I could make it disappear by telling Mathematica do the numerical solution in a different way, and it's going to look smoother. But it doesn't really matter. The point here was to confirm that the solutions are the solution of the approximate equation and of the complete equation are pretty similar. Now we're out of time, so I'm going to stop here, or at least close enough to being out of time. I've asked you for enough attention for today. We're going to close it here, and we're going to restart from here with our next lecture.